Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is an addendum to the derivatives of polynomials and exponential functions material, and I find that it's very important to let people know, especially if it's your first time taking a college course in mathematics, that in calculus, once you learn the mechanics of a derivative, it really is bad for you to just hand you a bunch of rote problems like mechanically compute this derivative and so on and so forth. At this point, the homework and the work that you're presented and the problems that you're presented should become more robust and actually involve a lot more synthesizing of older material. So that's what this video is going to be about, is all the oddball questions, actually not all, but some of the oddball questions that you can see when you're challenged with homework problems or projects or something like that. It is critical that you understand that you do actually have all the prerequisite information to complete these problems. It's just that they're not presented in a language that you're used to, so it always seems like a super challenge. There's no way your instructor can cover all of the possible material in these synthesis questions. These are the questions, for example, that are the last 20 or 30 questions in a homework set in the textbook. They're usually well above just mechanical knowledge. So let's go ahead and see how you could tackle these problems, how you could bring in older information and blend it with the newer material you've just learned to conquer these problems. Taking a look at this first problem, where does a normal line to the parabola y equals x squared minus 1 at the point -1, 0 intersect the parabola a second time? Anytime that you face a question like this, and it sounds confounding, like it's very confusing, very difficult to understand, the best thing you can do is draw a quick picture. It doesn't need to be perfect, because that's not what you're actually being graded on. You're not being graded on how perfect your picture is here. It's about if you can actually conquer this problem, if you understand the concept, if you can synthesize the material. And we were asked to graph the normal line to that curve. That's what I have shown here. The normal line to the curve at -1, 0. Maybe I should write that in just so that we can see that. And we want to know, when does that normal line intersect the curve a second time? And that's what our goal is here. So really the reason why I use my old algebra skills to graph this out, to graph a line, to help me visualize the problem, is so that I can tackle this problem, to make this a much easier problem. And now you start invoking some of your newer material. For example, what is a normal line? Well, we learned in a previous lecture that a normal line is the line that is perpendicular to the tangent line at that point. So for example, in this problem, we have a normal line to the tangent line of this curve at -1, 0. So the tangent line might look like this, and our normal line is the green line. So our goal is really to find out what is that tangent line first, so that we can find this green normal line, so then we can find when it hits, that green normal line hits the parabola a second time. So this is a very robust problem. Let's start by finding the equation of the tangent line. You don't even need the actual equation, you just need the slope of the tangent line. So if y is equal to x squared minus 1, then y prime is equal to 2x, and that's it, right? You bring down the power. This is the mechanical piece. Bring down the power off that x squared, so it becomes 2 times x to the first by reducing the power by 1, and the derivative of a constant is always 0. So y prime is 2x, and that tells us the slope of this black curve at any given moment, and we want to know what's the slope of that black curve at the moment x equals -1. So I'll just go ahead and write that out. So when x is equal to -1, y prime is -2. And that tells us that the slope of the tangent line at x equals -1 is -2. Now what we can do is start to build the equation of the normal line by taking the perpendicular slope. So that would imply that the slope of the green line, which is the normal line, is 1/2. Remember, it's the opposite reciprocal of the slope of the tangent line. And now we have the slope of a line and a point on the normal line. So now we have enough information to build the equation of the normal line. So this implies the normal line has the following equation. And of course, you would not want to leave it like that. You want to solve it for y if you can. It's not always the case that you need to do that, but it's a good idea to do that here. So you get 1/2 x, and then what is that, plus 1/2? So now our goal is to find out when does that equation strike the parabola a second time, or maybe I shouldn't say when does that equation, I should say when does that line strike the parabola a second time. And that just means you want to know when are their y values the same. So every step here kind of harkens back to our algebra days. So we want to know, and I'll write this over here, when does the normal line equal to the parabola? Now that's a weird way of saying that, but really we know that the y value for the normal line is 1/2 x plus 1/2. And we know the y value for the parabola is always x squared minus 1. So now we have an equation to solve. I'll multiply both sides by 2 because, well, I want to. I don't like the fractions there, so I'll just do that really quickly. And then after multiplying everything by 2, I'll gather all the terms onto the right-hand side of the equation. So we get something like this. And now all I need to do is factor and solve. And there we have it. This tells us that that equation, which tells us when the normal line is equal to the parabola, is true when x is equal to 3/2 or when x is equal to -1. And you can see that we already know the black parabola is equivalent to the green normal line at x equals -1. So the other solution is when x is equal to 3/2. It's right here. It's very nice. Now I'm just going to zoom out to see if they wanted the y value. They don't really specifically state that they want the y value. So if they don't state it, then I guess I don't need to find it. But I could easily find it because I have two equations upon which that point will lie. And so I'll go ahead and just plug it into the parabola. I'll have 3/2 squared minus 1, or 9/4 minus 1, or 5/4. So I'll just write that in here right here, comma 5/4. There we go. That is the point where the normal line intersects the parabola a second time. Now, as you could probably see from this problem, it seems very complex to begin with. However, this is the hardest part of calculus. It's not the calculus itself. It's the synthesis of all of the material up to and including calculus. So if you notice within this problem, we used the following skills. We graphed the transformation of a parabola. We found the equation of actually two lines. We recognize what to do when we have perpendicular lines as far as the slopes go. And we found when two curves intersect. All of those are prerequisite skills. And if you are missing any of those, or if you're shaky on any of those, then there's no way to complete this problem. And they are core to moving forward within this problem. I guess I should say the other thing that we did here is we factored. That's almost a gimme with all problems within calculus. You have to know how to factor. This next example demonstrates a future concept mixed with old concepts and current concepts. So this is a huge synthesis question. The equation y double prime plus y prime minus 2y is equal to negative 2x squared plus 14x plus 8 is called a differential equation. This, by the way, a differential equation, is the purview of a course called Differential Equations. And I often call that Calc 2.5 because most students should take differential equations after they have finished Calc 2. They can take it at the same time as Calc 3, but it is kind of important that you take it right after Calc 2. There's just a lot of concepts learned in Calculus 2 that get used immediately in differential equations, specifically working with sequences and series. Anyhow, this is called a differential equation because it involves an unknown function y and its derivatives, y prime and y double prime. Our entire goal when you're solving a differential equation is to find out what is the function y that I could take its second derivative, add it to its first derivative, and subtract twice the original function so that it becomes this parabola. Okay? So our goal is to find constants a, b, and c such that the function y equals ax squared plus bx plus c satisfies this equation. So the author of this question is telling us there is a solution to this differential equation, and the solution is actually a parabolic or a quadratic equation. We just need to know what are the coefficients of that quadratic equation. Let's start this problem with the current concepts. If they tell me that y double prime plus y prime minus 2y should turn into that right-hand side, then I'll probably want to find what y prime and what y double prime are. And in fact, I'll also want to write down what negative 2y is, even though that's kind of obvious here when they hand us what y is. But let's go ahead and find out what the first derivative of this function right here is. And I'm going to leave a little bit of space because I want to take advantage of writing something else down in a moment. I'm going to be writing down negative 2y in a moment. But for right now, let's write down y prime. Y prime, well, here is, right here, this is y. If you take its derivative, let's see, remember, an a, b, and c are just constants. So those are just numbers. So when you take the derivative of ax squared, you could just bring down the 2 from the power and subtract 1 from that power to create the new power. So you'll have 2ax to the first. In the second term, when you take the derivative of b times x, well, the derivative of x is just 1. So this is going to be b times 1, or b. And the derivative of a constant, as we know now, is always 0. So we don't have to worry about that. Now let's take a look at y double prime, the second derivative of y. And when you do that, you look at the first derivative here and take its derivative, the derivative of the derivative, if you will. So let's see, the derivative of 2a times x, well, the derivative of x is 1, so this must be 2a times 1. And b is a constant. The derivative of a constant is just 0, so that will not add anything else to our second derivative. Now I did write up here negative 2y only because we needed to insert into this upper equation here, we needed to insert y double prime, y prime, and a negative 2y. And I often find that it's much nicer just to write out what is negative 2 times y. This is more of an arithmetic problem. Just multiply each of these terms by a negative 2. So here we go. That'll be a negative 2ax squared, a negative 2bx, and a negative 2c. Zoom out so you can see all that. So now that we've gone that far, what the heck do we do, right? So we've done the current material, which is just taking derivatives. That's the extent of the current material for this problem. There's nothing else we would need to do from calculus for this problem. So what the heck do you do with this? Well, they want us to plug all that stuff into the equation. They don't explicitly state that, but that is actually true. They want us to plug y double prime and y prime and negative 2y into the left-hand side of that equation so that we can say, oh, that side, the left-hand side, is equal to the right-hand side. Now, the ultimate goal really is to find a, b, and c so that the parabola, or the quadratic ax squared plus bx plus c, would satisfy that differential equation. The way you would go about that, and this is why I'm including it in this synthesis video, because normally you just wouldn't know how to go about that. The way you're going to go about that is by plugging in those values into the first equation right there. So let's do that. Y double prime plus y prime minus 2y. That is equal to, now I'm not going to write the right hand side here. I'm actually going to write what that summation is, because I have all of those functions stacked right here ready for adding. So let's go ahead and add up y double prime plus y prime plus a negative 2y. And we're going to collect like terms while we do this. For an example, x squareds, I only have, and in fact, let me pause the video and shift some stuff. Now that I've shifted some stuff, it makes it somewhat obvious how I'm adding these things up. So as far as x squareds go, I have a negative 2a of them. Sorry, I have a negative 2a of those x squareds. As far as x's, I have a negative 2b and a positive 2a of them. And as far as constants, I have a negative 2c, a positive b, and a positive 2a. That's what the summation of y double prime plus y prime plus a negative 2y is. And notice how I collected like terms. It just makes it much cleaner. Now we want this, after we've added this stuff up here, we want that stuff to be equal to this quadratic, a negative 2x squared plus 14x plus 8. Let me actually write that down. So we want all this black ink on the left-hand side to equal all the green ink on the right-hand side. The black ink on the left-hand side is just y double prime plus y prime minus 2y. Now here's where a new method comes in. So we have so far only used current methods to just take derivatives, and then I used a little algebra to add some stuff up. Okay, that's old stuff. But now something new sneaks in here, and it's called comparison of coefficients. If two expressions are equal, then the coefficients on their like terms must also be equal. This is called comparison of coefficients. And what do I mean by two expressions being equal, then the coefficients on their like terms must be equal? Well, I mean that this negative 2 that's sitting on that x squared must be the same as this negative 2a. And I also mean, using a different highlighter here, this 14 that's sitting as a coefficient of that x must be the same as 2a minus 2b. And again, using a different highlighter here, this constant this constant 8 should be the same as that constant 2a plus b minus 2c. And when you see it that way, comparing those coefficients, you get what we call, in mathematics, what you should remember, a system of equations. So negative 2 should equal, actually maybe I should do it match up left and right. So negative 2a should equal negative 2, and 2a minus 2b must equal 14, and finally 2a plus b minus 2c must equal 8. The first equation is from relating the coefficients of x squared. The second equation comes from comparing the coefficients of x to the first. And the last equation comes from comparing the coefficients of x to the 0th, or in other words, the constant terms. That's comparison of coefficients. That's how you can find out what a, b, and c are. Notice this is a system of equations. There's no reason to set this up as a 3x3 system, honestly, because you could solve that first equation for a. So I'll go ahead and divide both sides by -2 to get that a is equal to 1. I'll box that up so I know that I've found it. And then I move on. If a is equal to 1, this will imply that we have 2 minus 2b is equal to 14, or in other words, a -2b is equal to 12. And then dividing both sides by -2, I get that b is equal to a -6, and I'll box that up. And finally, now that I have a and b, I can go ahead and plug those values into a and b on this last equation, and I will get the following. And this one I actually might take my time with. So this is 2 minus 6 minus 2c is equal to 8, or in other words, let's see, that's 2 minus 6 is -4. Add 4 to both sides, that's 12. So -2c is equal to 12. Or in other words, c is equal to a -6. So I'll write that in here. C is equal to a -6. And box that up and zoom back out. And we've actually answered the question, what is the quadratic equation that solves this differential equation? Well, that quadratic equation is the following. Y is equal to, I have to zoom in a little bit, y is equal to ax squared, so 1x squared, plus bx, which is -6x, plus c, -6. That is the quadratic equation that satisfies that differential equation. Within this problem, it was not only a synthesis of older material with current material, but it also was a preview of future material. The older material that we used here was a little bit of algebra, right? Adding up polynomials, and also solving a system of equations. Now, these can get kind of bulky, so you would have to solve 3x3 or 4x4 systems of equations. So you have to go back to solving systems by elimination or substitution, which is what we sort of did here. We used back solving, but same thing. So those are skills that are pertinent for this course. Now, finally, and I'm going to try to keep these end of section synthesis questions, the videos on synthesis questions, down to 3 questions, because honestly you could do a dozen or 24 of these and still not cover everything. So I'm just kind of doing highlights here to let you know that everything you actually see in your textbook or that your professor presents to you, you do have the prerequisite skills. It just forces you to think outside the box more, and mainly because you're in university level calculus, and that means you have to be able to create mathematics a little bit on your own using your older material mixed with your current material to synthesize all that. It takes it's a skill that you have to build up. All right, in this problem, find the parabola with that equation, ax squared plus bx, so there's no constant, whose tangent line at 1, 1 has the following equation. Now, this actually sounds worse than it actually is, but we want to find a parabola. I can't draw that parabola other than to possibly say that it opens up, but I'm not 100% sure it would. But we want to find a parabola whose tangent line, let's just pretend this is the tangent line at 1, 1. So notice that I'm sort of, whenever I solve a problem like this, I kind of try to draw what I can, even if it's wrong. I try my best to kind of give a visual of what's going on. And we want that tangent line at that point to have the equation y equals 3x plus 2. All right. So again, I'm not telling you that that's what the parabola looks like. I'm just saying this is one possibility. The next thing we'll need to do is identify what we're actually looking for. We're looking for A and B here. Let me get my right highlighter in here. We're looking for A and B. Those are the unknowns in this situation. And so that's going to require a little bit of creativity to help us find those. And we're given the equation of the tangent line that touches our curve at the point x equals 1, y equals 1. Now, the fact that they tell us we have a tangent line at x equals 1, y equals 1 invokes a prerequisite skill. If I told you that you had a parabola that went through 1, 1, then you should know that if you plugged x equals 1 into the equation for your parabola, the output, the y value, should be 1. So they are subtly giving you a value and helping you find A and B here. So just from that, you should be able to say, okay, so when x is 1, y is 1. That is, for our equation right there, I'm going to let y equal 1, and I'm going to let x equal 1. So we have one equation down. The rule of thumb in mathematics is the number of unknowns you have should match the number of conditions you have. So you have 2 unknowns, you should have 2 conditions. And a condition in mathematics is represented generally by an equation. So if you have 2 unknowns, you want 2 equations. We have one equation down. Yay! Now the next one is to look at the fact that they handed us the equation of the tangent line. So notice I've already used the point 1, 1. Now I have this equation just hanging out waiting to be used. I don't actually need the entire equation, at least not that I think right now. But I do know one thing about that equation. Its slope is going to be the derivative at x equals 1. Again, because this equation of the tangent line touches our curve at x equals 1, the slope of that tangent line should match the derivative at x equals 1. That's the whole point of a derivative. The derivative is a slope of the tangent line at the point. So let me write that down. This implies f prime at 1 is equal to 3, where f of x is our parabola ax squared plus bx. I was going to write something else. So I want to show you what I was going to write here. I was going to write, this implies that y prime at 1 is equal to 3. The problem with writing that is that y is defined twice, here and here. And so it's ambiguous if I said y prime at 1 is equal to 3. I need to label one of those equations separately or differently. And so that's why I decided, you know what, I'll just label the parabola f. And that way, when I say f prime at 1, you know which function I'm talking about. It's just a little bit of a something to observe anyhow. So if f prime at 1 is supposed to be 3, then that tells me I should probably try to find what f prime is. And that's pretty easy. F prime of x is equal to, remember a and b are constants, so the derivative of a constant times x squared is 2ax to the first, plus the derivative of b times x is just b. And we know that if we plug 1 into that, our output should be 3. So I'll plug 1 into that and force the output to be 3. And notice what we have, yet another equation involving a and b. So I'm going to invoke my prerequisite skills to note that once I have 2 equations, both with a and b in it, I now have a system of equations that I can easily solve. This time, as opposed to the last example where I did back substitution, this time I'm going to do elimination method. So let me go ahead and write out the equations. A plus b is equal to 1, and 2a plus b is equal to 3. And what I'll do is I'll just take row 1, I'll subtract off row 2. That will kill off the b values. So a minus 2a is a negative a, b minus b is 0, and 1 minus 3 is a negative 2, which implies that a is equal to 2. And finally, take that value and substitute it into either equation. I'm just going to substitute it into the first equation because it's much easier. And that would tell us that b is equal to a negative 1. Let me just double check that. Yep, that's exactly what it tells me. So now that I've found a and b, I can go back and answer the question. Find a parabola with equation y equals ax squared plus bx, whose tangent line at 1, 1 has that equation. Well, we found that parabola. That equation is going to be y equals 2x squared minus x. That's supposed to be an x, but it didn't work out. There we go. That answers the question. So note, when we did this problem, again, we're using current material, which is derivatives, but only briefly. And that's what's the hard part about calculus, is that it's used in spurts, but all of your algebra gets used quite a bit. So part of this problem was recognizing what the graph of a parabola is, knowing that if you have a point on that parabola, 1, 1, that means that you could plug that into the equation for that parabola. That's what we did here. It also involved current material by saying, well, if you have a tangent line at that point, 1, 1, and you know the equation of the tangent line, then you know the slope of the tangent line, which means you know the derivative at 1, 1. And now that you know the derivative at 1, 1, well, then you can take the derivative of your function and substitute in x equals 1 and y equals 3. And now you're solving, again via algebra, a system of equations. All of this is a mixture or a synthesis of current and prerequisite material. So I hope this video is somewhat helpful. I just want to really drive home the point that as you move through calculus, you're going to continually reach back and into older material and bring it into your current course. And it won't be as if your instructor said, hey, in this situation do this, and in this situation do that. It doesn't work like that. It's assumed that you have seen all your prereq material and that you are mastered, that you've shown mastery of that material. And there's no way for your instructor, especially in calculus, to cover any of that material because opening that Pandora's box would be terrible. So I hope, again, that this was helpful.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.